So this is a zero lesson for our non-equilibrium stochastic process course. It is just a recall of equilibrium statistical mechanics. I shall revise the postulates of equilibrium, entropy, and the derivation of the second law of thermodynamics, coordinates, and statistical ensembles, and finally some consideration. So, for a continuous deterministic and dynamical system, the natural space is the phase space that can be defined as by means of general coordinates and general momenta. Coordinates can be both spatial coordinates, angles, and so on. In general, these their value evolve according to some function that may depend on p, q, and t. But if the system is conservative, energy when closed is conserved, and so there is a function which gives which is a constant. The energy does not depend on time, and in this case, the equation of motion are given by the derivative of h with respect to the conjugate variable. Clearly, given an initial condition, we get a trajectory in the phase space, and we have to study which are the conditions for which this trajectory spans the whole system or not. For instance, here we see a phase space portrait. I mean, it is a section of a three-dimensional system. When you see these circles, it means that we are crossing quasi-periodic solution. So essentially, here we see some chaotic trajectory, so we can think that starting from any point we will explore all these phases. But clearly in this situation here, we do not have any possibility of escaping the limit cycles. Then, since the energy is conserved and the motion is deterministic, the trajectories cannot join exactly together, nor can split one trajectory, because otherwise it would not be deterministic. And this brings to the Liouville theorem that says that if I take an initial condition of my system and let it evolve, the volume of this, the number of trajectories essentially remain the same. Clearly, the volume can be stretched or can be also deformed. This is the case, for instance, of free falling objects. And clearly, we do not pretend in statistical mechanics to follow all trajectories, but to give a statistical description of what happens to our system. And we try to impose the minimum number of constraints necessary to derive some consequences. One of these is, for instance, for a closed system, a conservation of energy. We do not generally impose the conservation of momentum and conservation of angular momentum, because the boundaries essentially interfere with that. So the postulates are a few. The first postulate is for closed system in equilibrium, are that all states are equiprobable, in the sense that we should be careful. We have to take our system, use a kind of coarse graining of the system, so that we have a say innumerable number of cells. Then we assume that a trajectory starting in any of these cells will explore all the available space, such that it spend essentially the same time in any of these cells. Clearly, we can also think of taking a bunch of initial conditions, and this is a slightly different condition, taking a bunch of initial conditions to have this bunch diffuse for all system. Actually, we could we could also design a system which systematically travels all cells, and so that it passes the same time in each cell without having these mixing properties of spreading. But in general, this is quite difficult. And so clearly, for instance, a classical example is that of a sequence of head and tails. Clearly, we see that any microstate is equally probable, but clearly when we then classify this set according to some observable, for instance, the number of heads and the number of tails, we have combination that are represented by more in microscopic configuration, and others that are represented only by a few microscopic configuration. Clearly, when we say that all states are equiprobable, we are considering individual microstates and not observables. The second postulate, which is related to the mixing property, is that the system will explore the whole system and not in a systematic way, so that a perturbation can expand to whole system. This is to ensure that in the long time limit we do not have to care about initial conditions. Clearly, we can have a mechanical system which are, say, ergodic for a given initial condition, not ergodic for other. For instance, this billiard is not ergodic if we start the ball bouncing in a given condition, maybe ergodic in other conditions. Clearly, it is not so easy to devise what happens in a system. For instance, one could think that a system like this would drive the particles all in the second part, but actually this is not true. And clearly this sense, this invariance of the final configuration is related to the second law of thermodynamics, that essentially says that the system always evolve towards equilibrium when possible. So, to be more formal, we shall introduce probability distribution in order to have a mathematical sensible distribution. We have to partition the system into a certain number of cells. This is because if we take a real deterministic system, actually, and we make the cell so small that only one possible condition is inside our system, then we have a trajectory that simply explore the system, but we do not have a distribution of probability, because the probability is always concentrated on a single cell. Otherwise, if we take a coarse-graining cell, and so we have more than one or many conditions for each cell, then after some period we can find these instances distributed along the system, so that the information is more distributed. And clearly this has to do with the second law of thermodynamics. Okay, so let us indicate with the qk, pk the coordinates of a cell. A cell normally is defined profiting of a quantum system that says that there is an uncertainty principle for which two conditions cannot be distinguished if they are close enough. And so, in general, we take this coarse graining given by the uncertainty principle, but this is not compulsory. We can use other different coarse graining. And so, clearly, we can start from a selected set of initial conditions. For instance, we can select a given portion of the phase space and start from there. And so we want to examine how this information concentrated in this portion will evolve to the whole system. Okay, so let us define more formally the probability distribution. So the probability of finding the system in a given cell, which means finding the coordinates inside, so around the coordinates of these cells, or being equal once that we have discretized these coordinates, essentially means constructing an histogram, so summing how many of our replicas are inside a given cell. And as we said, one of the postulates of statistical physics is that if I have a closed system and considering all cells that describe the system with the given energy, then the probability of finding a given configuration is the same for all configurations, so that the finally the probability distribution is just 1 over the number of possible cells. Clearly, we are more interested not in the just probability distribution, but in observables. So we can define an observable as a function of coordinates, and what we do with in an experiment is to measure the average value of this observable after some sampling of the system. So it means taking the average in time. Actually, we want to replace this average in time with an average over the probability distribution, an average on the phase space. Clearly, assume that we are able to obtain the probability distribution. And so this is called the ensemble average. And the other assumption of statistical mechanics is that in the long time limit, when if the system is ergodic to visit all the possible space, then the time average and the phase average are the same. We shall revise this postulate at the end of this lesson. Clearly, this cannot hold for a linear system, because a linear system can be divided into normal modes. So, for instance, suppose that the energy is the sum of the energy of two variables that are uncorrelated, so that the probability distribution of one variable does not affect the probability distribution of the other variable, so that the probability distribution is just the product of the two probability distribution. And so, for instance, there is no way of thermalizing the system, so to arrive to a given situation independently of the initial condition, because clearly if I change the initial condition in one of the two subsystems, the other is not affected. Okay, now let's try to port what we know about thermodynamics into this representation. First of all, we have to define entropy. Energy is quite easy because it is a natural concept also in our dynamical system, but entropy not. Clearly, we want, first of all, to have extensivity. For energy, it is already clear that if I have a system composed by two subsystems, I say almost non-interacting because, as I just presented in the previous slide, I need some interaction between these two parts. Otherwise, they do not thermalize. For instance, they do not arrive at the same temperature. But assume that mainly two systems are non-interacting. This also may be implied by the fact that if you think of two systems of particles, if the interaction range of particles is finite, only those particles that are within this range at the boundary of the two systems interact. And clearly the energy is dominated by the bulk energy of the two subsystems, and I can for the moment forget the energy due to contain the interaction among these two parts. So we can assume that energy is an extensive property, and we also want the the entropy to be an extensive property. But if the two systems 1 and 2 are not interacting, the probability, the joint probability of the two systems is just a product, except for some other term, of the two probabilities. So clearly it is reasonable to take the entropy as the logarithm of the probability so that it becomes extensive. So we introduce the information entropy, which is P log P, which is essentially the entropy is the expectation value of the logarithm of P. And clearly you can check that if P is the product of P1 times P2, clearly logarithm of P is logarithm of P1 plus logarithm of P2. And then when I average this and this over the product of 2, I only get the average value logarithm of P1 plus the average value of the logarithm of P2. And clearly, from a practical point of view, I can also use integrals provided that the volume of the phase space is measured in unit of some action, in particular h or h bar. This only affects a constant of our entropy. Clearly, if we have a complete information, so I know that all the variables are inside the cell in my system, so I know that they are all here. Clearly, the probability of this cell is 1, and the probability of all other cells are 0. I extend this product taking the limit, so 0 log 0 for me is 0, and so in this case the entropy is 0. It means that the information is maximal. While if the information is 0, so I just know that the system has the same probability of being in any cell, so the probability of a single cell is 1 over omega. Omega is the number of cells, and the entropy is maximal and is the logarithm of the volume. This is also the formula which is on the Boltzmann grave. Entropy is special because while other observables, like, I don't know, pressure, energy, and so on, are things that are defined also for the dynamic version of my system, and I compare time averages with ensemble averages, entropy is only defined for ensemble averages. There is no little sense in speaking of entropy of a single system, and so we have to consider a probability distribution for defining the entropy. Clearly, we up to now we always have used the natural units for which the Boltzmann constant is 1, but if you want to identify information entropy and real thermodynamic entropy, we have to multiply entropy by this constant. And as we have seen, for a closed system, entropy is also related to the measure of the accessible space in the phase space. Now we want to apply the second law of thermodynamics, I mean maximizing the entropy S with a certain number of constraints. One constraint, for instance, is the sum of the normalization of probability. The sum of all components of probability is 1. Why? So, because since it is difficult to do maximize things with a constraint, we use Lagrange multipliers so that each component P of k can be considered as an independent variable, and we can just maximize S minus lambda times the constraint freely for each component. And clearly this gives simply that P is a constant, and as usual for Lagrange multiplier, when I insert the normalization, I get again what I expected, that is that the probability distribution for a closed isolated system is a constant equal to 1 over the number of accessible states, once that I use the coarse graining in the phase space. Clearly, we can now switch to a system which is in contact with the heat reservoir. I mean, the idea is that you have a very big isolated system, but you are considering only a fraction of this. We can exchange energy with the rest of our system. In this case, the other constraint is that the energy can fluctuate, but in average it is fixed. Then we introduce another Lagrange multiplier, and now we find that the p logarithm of p is proportional, is related to the energy. The other this can be substituted after the computation by inserting the normalization condition. So we find that this P is proportional up to some constant to the energy, and once that we insert the normalization condition, Z is the sum of x of minus beta e of k over k, we have essentially we determine the value of the other Lagrange multiplier. Z is called partition function. So if now we put this distribution into the definition of entropy, we find that we have this, which is clearly beta and the average value of the energy, so beta u. And here we have the average value of the logarithm of z. Let us now derive, using similar consideration, essentially maximization of entropy, the relationship between thermodynamic coordinates like temperature, pressure, volume, and so on. Let us now consider what happens if we have a closed container divided in two portions, which can communicate energies. They are divided by a conductive wall. So we impose extensivity of entropy and extensivity of energy, and the fact that the two volumes, they can be equal, different, and the two number of particles essentially are constant. The second law of thermodynamics imposes that the entropy has to be, the total entropy has to be a maximum. If there is a small amount of energy that passes from 2 to 1, the energy of system 1 increases and that of system 2 decreases of the same amount. So we impose that the variation of the total entropy with respect to this fluctuation is 0, and this means that the variation of the entropy of system 1 with respect to energy 1 and the system plus the difference of system 2 to the same difference of energy, which is minus delta dA2, are equal, are the sum is 0, so that these two, the sum of these two is 0, and this implies that this condition is equivalent to the fact that the derivative of entropy for with respect to energy for the two subsystems is the same. So since the zero principles of thermodynamics says that when two systems are in equilibrium, they have the same temperature, this means that this quantity here is a function of the temperature. Clearly, if we want to keep the parallel with the thermodynamics, we see that this quantity, which is in thermodynamics 1 over T, is our Lagrange multiplier beta, and so beta is the inverse of the temperature. Now, if we come back to the relationship that we have seen before that relates to the average energy, which is considered equivalent to the internal energy, the entropy multiplied by now the temperature are equal to minus t times logarithm of z, but since in thermodynamics this is the definition of the free energy, it means that the definition of it means that the free energy is equal to minus t times the logarithm of the partition function. And since in thermodynamics we know that from the free energy we know everything of the system, this means that one of the goal of statistical mechanics is to compute the partition function, which is a function of the thermodynamic variables, I mean volume, number of particles, temperature, and so on. Clearly, this is also the function that has to be minimized without constraints. The conclusion is that equilibrium corresponds to the minimum of the free energy. We can repeat the same argument for a variation of volume. In this case, again, we impose extensivity of entropy, extensivity of energy, and also the extensivity of volume. Now, I assume that both systems are in equilibrium for the thermal part, so they have the same temperature. Now, we have for a variation of volume that the variation of first part of the container increases while that of the second part of container decreases, both for energy and for the volume. And so that maximizing, we again have this as before, but now we have also the equivalence of the derivative of the entropy with respect to the volume. And so, since this is a mechanical equilibrium, it means that it is a function of the pressure. In order to find explicit expression for the pressure, consider that if we take the first law of thermodynamics for in the adiabatic process, which means fixed entropy, and clearly we always consider the number of particles constant, the pressure is related to the work done on the system, which is also related, since we have no heat transfer, to the variation of the internal energy. Now, this relationship is valid for all for all three tuples of variables, and so if we now set this z equal to 0, we find this relationship. Z is constant, and z equal to 0 means z constant. So we have this relationship between any three variables which can be considered, which are related by some relation, so that each of them can be considered a function of the other two. And therefore, since we have already this one from this, we use this relationship in order to insert this one by inverting this. And so this means that we have this function here. And since we already know that this is the temperature, we have that the variation of entropy with respect to the volume for constant internal energy divided by the temperature is the pressure. Clearly, the relation P, now I insert also the constant number of particles, means that the pressure is something that is related to the changing in the volume, keeping entropy, and so forbidding passage of heat constant. And this clearly implies keeping the distribution constant, because you know the entropy is the average of the logarithm of p. And this means that since we have to change the energy means changing the energy levels. So if I have a particles distributed to a certain number of energy levels and I want to change the energy, I can clearly change the distribution of particles, but this would change P. Or I can simply shift the level on without changing their population, and this would change the internal energy. And since the internal energy is the average value of the um, energy, clearly I can have a variation of energy both because I change the population or because I change the energy level. I say that I do not change this here, so it is just this variation here. And so since the pressure is the variation of the energy with respect to the volume, which is equal to variation of energy is equal to this, I put inside this one. So I obtain this this expression here for the microscopic value of the pressure, which means that the pressure is equivalent to the shift of the energy levels when I change the volume, keeping entropy, the population, and the number of particles constant. And so essentially we can also say that the variation of the energy of a level is given by the pressure associated to this level times the variation of the volume. And so finally, the variation of the energy, which is the average of the variation of the level weighted by their probability distribution, is essentially, we can replace this with this, so we can have a microscopic definition of the pressure for each energy level. Then let us take the consequences of the free energy. Clearly, this is the definition of Helmholtz free energy. This is the first principle when expressed as a variation of energy and work and the energy related to particles, in case we assume that we can variate also the number of particles. And so by taking the differential of the of the free energy, putting then there both the variation of heat and the variation of heat and the variation of energy, we obtain this set of differentials, and therefore we can define the pressure as the derivative of the free energy when temperature and number of particles is constant. The entropy as a derivative of the free energy with volume and number of particles constant. And finally, we can also define the specific heat, the internal energy related to this derivative, and also the specific heat related to the second derivative of the free energy and the chemical potential. So essentially I can derive any thermodynamical quantity once that I know the free energy, which means once that I know the partition function. Let us just make other considerations about the free energy. Clearly, we know very well the ideal gas law, but this does not include intermolecular forces or exclude the volume, so cannot reproduce, for instance, the liquid state. A more detailed model is the van der Waals one, in which one considers also that in a fluid there are both permanent dipoles, like for instance the water molecules. Or we can have oscillating dipoles due, for instance, to quantum uncertainty. So these are attractive forces also present in noble gases and so on. Also, say, argon can condensate at the end due to these intermolecular forces. Now, since the force on a dipole depends on the crisis as the 1 over r square, the cube of the distance, the energy due to dipole-dipole interaction decreases as the sixth power of the distance. And in order to express this as in terms of on thermodynamical coordinates, we can consider that the volume divided by the numerical density is proportional to the average distance between a molecule to the cube, so that finally we see that the extruded volume decreases the actual volume. These intermolecular forces essentially affect the pressure, so that the effective action is not only due to the external pressure, but also to intermolecular forces. And so we arrive at this van der Waals equation that actually coincides almost with the ideal gas law at high temperature, but then it starts to show a critical temperature, and then this phase that corresponds to the crossing between gaseous phase and the liquid phase. This part here actually it is considered it is unstable because there is a negative say derivative of pressure with respect to the volume. So it is a negative force in some sense, a force that tends to collapse things. And actually, since we know that the pressure is the derivative of the free energy with respect to the volume, this negative part here means that the free energy has a concave part in in this region. And this means that if I take these two parts corresponding to liquid and to gas, and so the free energy is actually lower if instead if I take the actual value forecasted by the van der Waals equation, I take a mixture of the phase A and B. This means that as soon as we impose homogeneity of the system, we have the van der Waals representation. But if we let the system evolve themselves, it simply separates in a liquid phase and a gaseous phase, so that the energy is actually minimum. Clearly, the real free energy is not this line, it is some which is slightly more convex, because there are still intermolecular forces between the liquid and the gaseous phase, which decreases further the free energy. Repeating the maximization of entropy, allowing also to the number of particles to fluctuate, but keeping the average constant by means of a mechanism that can inject or remove particles from the system, for instance, a chemical reaction. We need the third Lagrange multiplier, so now we can maximize the entropy with respect to normalization of probability, which is the temperature, which is the first constant. Then minimization, keeping constant the energy, which is related to the temperature, and keeping constant in average the number of particles, which is related to the chemical potential. And this is clearly if we have more than one species, n, and therefore the chemical potential may be different for different species. So actually, instead of the single product, we have to consider the sum of the product of the two quantities for each of the species. And as beta is the derivative of energy with respect to entropy, the chemical potential is the derivative of energy with respect to the number of particles. This introduces a new partition function because now we have to sum also over the number of particles. So essentially, we have to average the partition function of each realization of a system for a given number of particles by this weighting factor, and this is called the gram partition function. And it is related to another thermodynamical potential that can be obtained using the classical transformation of potentials. So essentially adding this term to the Helmholtz free energy, and if one now replaces, sees that the grand partition, the grand potential is simply minus PV. Clearly, we can again derive all quantities as derivatives of this new potential, and so we obtain that if we want to work in the grand canonical ensemble, then we have the pressure, entropy, and chemical potential as a function, as derivatives of this potential. Okay, now let's switch to statistical ensembles. The first one we have already seen is the macrocanonical ensemble, which means that we are working at constant energy, and that the probability distribution is just 1 over the number of accessible states, while the entropy is just a logarithm of the number of accessible states. The problem is that it is not so easy to work in the canonical ensemble. Let's present an example. Just the simple ideal gas model, in which the energy is just the sum of the kinetic energy of each particle. We have to compute the entropy, so we have to compute the volume of the phase space, and this is just the volume of hypersphere, which is not so easy to compute for n dimensions. So clearly the hypersphere has a radius which is the square root of the energy, and so we can see, looking at the formula on the internet or deriving the integrals using essentially the definition of the gamma function, we see that the volume of this hypersphere is given by this formula, and therefore the surface of this sphere is given by the derivative of the volume, which means we have this formula. We can see that the surface A is related to the differential of the volume, but there is also little difference between surface and volume, especially for an electric sphere in many dimensions. All the volume is in the spherical crust at the maximum radius. In any case, this is the expression of the volume of the hypersphere, and we divide by n factorial in order to take into account the indistinguishability of particles. And then, using a Stirling formula, we finally obtain for the entropy this expression, which is the Sackur-Tetrode state equation that essentially contains both the real state equation PV equal to nRT and the definition of the specific heat. Notice that the factor that we introduce, n factorial, is fundamental to have a term n log of V over n, still keeping the entropy extensively proportional to n. Otherwise, things do not come back right. And why we should introduce this fact that is called Gibbs correction factor and is related to the Gibbs paradox. The fact that if we consider, for instance, a container containing a gas which is divided into two portions, with a set that is divided into volumes, and then we remove the set and we let the system to mix together, clearly entropy should increase, but not so if there is the same gas in the two portions. This is, in some sense, related to the fact that we we are assuming that we do not want or we do not can or we cannot distinguish between a position, a particle in a given position or an identical particle in another position. And so if we do not measure, do not take into consideration these possibilities, we have to assume that in this case entropy is not increasing, and in order to recover this, we have to divide by the factorial of n. And so essentially this is again the same concept. Actually, this is a result that in some sense depends on the opinion, on the willing of experimenter to distinguish or not particles. For instance, we can have two different kind of gases, but we do not care about distinguishing them because they are the same. I don't know. I can have nitrogen and I don't know, carbon oxide and dioxide that are almost inert, and so when they are mixed together, nothing changes. Or we can have two isotopes of the same material that could be distinguished, but we do not want or we cannot do that, and so we consider that the mixture has a higher entropy. So the entropy for a given energy per particle is given by this expression here. And in the first case, when we mix two different gases, the entropy changes. So the variation of entropy is given by essentially this correspondence between number of particles and volume before and after the transformation, while in the second cases delta S is equal to 0 since this density is considered constant. So essentially this is the reason of why in the first case we have an increase of entropy, because the density of the two portions are supposed to decrease, while in the second case the density is not supposed to decrease. And then, as I already anticipated, this also means that entropy has a subjective interpretation, not always just a physical one. We can also have negative temperatures, because since temperature is defined as the logarithm of the entropy, the derivative of entropy means the derivative of the logarithm of the number of states with respect to the energy. If the number of states always increases with energy, for instance, for a perfect glass case, we have seen that the the volume of the phase space is essentially the volume of an hypersphere that has a radius that grows like the square root of E. So in this case, the phase space is always increasing when one increases the energy. But for instance, if we have spins or we have a laser with a population on two levels, I see that the number of configuration, first of all, is 1 if all, say, electrons are in the ground state. Then there is n state with one electron in the upper state and all the others in the ground state. Then the number of states increases, but at a certain point, when they have a same number of electrons in the ground state and the excited state, and I pump other energy into the system, the population start to become more larger in the upper state than in the lower state, and the entropy decreases. And this corresponds essentially to negative temperatures, which are essentially more hot than positive temperature. Or negative temperatures are hotter than positive temperature. It means simply that our axis, temperature axis is wrong. We should have used another axis where, for instance, the absolute zero is, say, at minus infinity. Okay, so we can also perform some computation. Let's suppose that the energy is given by this expression here, depending on how many are in a ground state or in an excited state, or speaking of spins, in the orientation parallel or antiparallel with respect to the external magnetic field. So the number of microstates is simply given by the all possible permutation of the system. Taking the logarithm of this, we see that the temperature, the derivative of the logarithm of omega with respect to n, can be negative if there is an inversion of population, if the population in the excited state is greater than half of the total population. We have seen that in the microcanonical ensemble we have to fight a lot against factorials and permutations. So it is much easier to perform computation in the canonical ensemble, in which we keep n and v constant and also a temperature, but the energy can fluctuate. And so clearly we can also think of the canonical ensemble as a small ensemble inside a big microcanonical one. And so, assuming that the interactions, as usual, are negligible, we have that the total probability distribution is the product of the probability of the microcanonical and of the canonical ensemble, so that after some computation we see that essentially the probability of the microcanonical ensemble is, as we can expect, the exponential of the energy. And so this means that we can have this probability definition, but clearly normally one want to not to consider the microscopic configuration, but for instance energy levels. So group microstates according to some observable, for instance the energy. So we have to introduce the degeneracy of the state and the probability distribution in terms of this grouping of these classes are given by this formula. Clearly, if the system can be divided so that the energy is just the sum of the energy of the two subsystems described by two different variables, then the partition function simply factorizes, which means that the free energy is the sum of the free energy of the two systems. Notice that actually we used the same temperature for the two distributions, which means that the two systems are slightly interacting. Otherwise, we cannot have the same temperature. If we want to compute the classical ideal gas in the canonical ensemble, this is the expression of the energy, which is given by a sum of different variables for each different degrees of freedom, which means that the partition function is just the partition function of the single molecule and single direction to the power n. From this expression, we can derive the free energy, which clearly is proportional to the number of particles, and then we can derive all the usual things. You see the specific heat, which is minus 3 half, because we have considered only 3 degrees of freedom. The pressure, which gives the standard state law of the ideal gas, and again the Sackur-Tetrode formula for the entropy. We can reconsider, for instance, the two-level system that we have seen in the microcanonical ensemble, and again, if we do not consider the coupling among spin, but only their interaction with the magnetic field, again, we have for the partition function, just the partition function of the single particle raised to the power n. And so, for instance, we have this for the quite simple, because we have just to sum two terms for the partition function of the single particle. The probability distribution is this one, and the average magnetization is given by this hyperbolic tangent, which is also the derivative of the free energy with respect to the magnetic field. So again, we see that if we know the free energy, we know everything of the system. And we can also consider the Maxwell distribution for the ideal gas. So if the ideal gas is made by indistinguishable particles with a given mass and momentum, then this is the energy of a single particle, and we have to sum over all of them. And so this is the expression for the probability distribution. Again, the partition function is just the product of partition function of all particles, so is the n power of the partition function of the single particles. And so again, we have this simple expression for the probability distribution. And in terms of velocity, we can recompute the distribution in terms of the modulus of velocity, and we get this standard Maxwell distribution, which is a curve with an exponential tail, and whose maximum increases when the total energy increases. Clearly, the equipartition theorem says that the average energy per particle and per direction is per particle per direction is 1/2 t, and per particle is 3/2 of t, which again gives the specific heat. The internal energy is again given by the derivative of the free energy with respect to the temperature, or this one. And the fluctuations, you see, are essentially related to the specific heat. So this is a general result that fluctuations and correlations are related each to the other. And clearly, the relative fluctuation decrease with the square root of n, and this means that if we have a large enough system, quantities do not fluctuate. And the pressure relative to a microstate we have already seen is this one. And again we can find all the relations that we have already seen. It is just a reformulation of things. And also the entropy can be derived from the free energy function. Let us, for instance, apply this to quantum statistics, because the idea of statistical mechanics is to perform the sum of all possible configuration according to the constraint of the system. In the case of quantum mechanics, we have to insert the constraint typical of quantum mechanics. So suppose that and x and y and z are the quantum numbers associated to such level, and that the energy is simply the sum of the square of this quantity. Essentially, it is a free particle in a box, while levels are given by the size of the box, which if we use a cubic box, it is the volume to the 2/3. So the single particle partition function is essentially very simple. We have just to sum these Gaussians over all the quantities, and so we obtain this this expression, which clearly is the same obtained for a single particle in the classical gas. So we have proven that the quantum statistics in the limit of large volume, so that we can approximate the sum with integrals, are the same as the classical result. Finally, we can also examine what happens in a grand canonical ensemble, in which also the number of particles can fluctuate. And we have seen that we can define an potential for this ensemble, which is called the grand potential, and that we can obtain the all the quantities deriving this potential, which is the logarithm of the grand partition function. So we can think of a system of independent particles, so that the population of a part of a level is not does not influence the population of another level. Each level has a certain number of subsystem, some levels g of k, and on each of them there can be a certain number of particles. So for instance, for fermions we only count say one particle for each sound level. For bosons it can grow up to infinity, and so we can compute the grand canonical partition function simply summing in the right way the number of the generation and the number of population for each sublevel. So we obtain this for fermions and this for bosons, in the sense that in one case the sum goes from 0 to 1, and in the other case from 0 to infinity. And in the for fermions, the partition function, as we have seen, is this one. This means that the average number for part for level is given by this function here, which has this shape according to the temperature. Clearly, we could have obtained the same result by taking the derivative of the partition function instead of working on the probability distribution. And on the other hand, for the Bose-Einstein distribution, computation is similar, but the function is different, so that we have different results for the Fermi-Dirac, Maxwell, and for Bose-Einstein distribution, or number of particles, average number of particles. And it is evident the advantage of using the grand canonical ensemble. Instead of working on with a fixed number of particles, we can let the particle change so that we can sum over the occupation number. In an ideal Fermi gas, this is the average number of particles per level, and so we can add the degeneracy due to the spin 1/2. So in terms of the energy, we have this expression, and so finally the number of particles per energy level is this one. So the total number of particles is this, from which we can get the chemical potential needed to impose the number, the desired number of particles. And we can clearly derive also the energy of the system, at least in a formal way. And to compute the pressure, we use the result that the energy depends on L to the minus 2. It means that to the volume to the minus 2/3, so that the derivative of the energy with respect to the volume is just minus 2/3 the energy of this level divided by the volume. And as usual for all ideal gases, we have this state equation in terms of the energy, PV equal to 2/3 energy. The grand potential is given by this expression here. You can again check, and with a lot of computation we can obtain the entropy of a Fermi gas, which is this one. So at low temperature all energy levels are occupied, and this defines the Fermi level, which is the chemical potential at zero temperature, where for each small amount of energy that they put, one of our particle, one of our electrons, abandon the all occupied sea level to jump to the first available level. The pressure of the generated Fermi system is related to this expression for the energy, and so finally we can find the total number of particles where we introduce the Fermi level here, and these are the classical distribution for the Fermi system. While we can use what we have already obtained for bosons to derive the relation for the black body. In this case, we have the relationship between energy and momentum valid for photons, which is this one. And clearly the number of photons in a cavity is not constant. They are emitted and absorbed. So we have to define a chemical potential which for photon is essentially zero, because we can essentially absorb or re-emit a photon without any change in the energy except for the energy of the photon. And so we get this expression for the number of photons of a given frequency, and since we have to introduce the degeneracy due to the essentially the same relationship as for a set of the integer positions inside the sphere of a given radius, and finally we get the expression for the total number of photons of a given frequency, or the energy of a given frequency, which gives the Planck formula. And this is also the Planck formula expressed in terms of the wavelength. And while in the classical theory of in which each um, oscillation of the electromagnetic field is considered as the same level, so can store the same amount of energy, the equipartition theorem, and we have this infrared divergence by inserting the fact essentially that the quantum of energy is related to the frequency, so that the quantum of energy is h omega, or h bar omega. And in this way we cannot populate the modes of high energy if the total amount of energy is small enough, and so we get this black body curve, which is a kind of bell curve whose maximum increases with the total energy. So final configuration, there are some points to be considered. We often see pictures like this. This is a likely distribution. This is a highly unlikely distribution. This is not true. All configurations have the same probability. The fact that we are not considering this as a particular configuration, but as a typical configuration of a certain class of conditions. So clearly, if we move one of these in here, nothing changes, while if you move this here, the picture changes. So essentially, we have to consider that we are often considering the classes and the specific configuration of particles, and also the fact that we assume, often without stating explicitly, the indistinguishability of particles, so that, for instance, if we exchange two of these particles, we consider the figure to be essentially the same, while for instance, if we put a different color on each particle, I could distinguish between two different configurations. Also, ergodicity is not a simple problem. Suppose that we are measuring, observing, or simulating a gas that has a low temperature, so that it tends to condensate in some cluster. Then clearly, while in the high temperature phase, all the space is accessible, so that the system has essentially an ergodic character. In the low temperature phase, the gas condensate in a zone and not in another, so that the ergodicity is broken. And this also means that if we follow the evolution of the system, one should say for a certain initial condition, the system goes in one condensate, and for other different initial condition, the system goes in another place. And clearly, this can be done both experimentally and in simulations. But for instance, when we perform a certain kind of parallel simulations of a whole system, it may happen that the actual trajectory samples all the available space, which means essentially that in the case of a phase transition, I have the probability distribution, for instance, which is given, say, suppose this is the free energy landscape, so that the probability distribution is essentially all connected. when the free energy develops a high energy barrier here, or a large difference in the two phases, the probability distribution can factorize into two probability distribution, one concentrated around a minima and the other concentrated around another minima. Now, if we follow the evolution of the system, starting from an initial state, I should say, see evolution that essentially is trapped into one of these two probability distribution. But nothing forbids to have large jumps from one to the other and to sample both the two branches of the probability distribution. And this is possible clearly in numerical simulation, especially if I find a way to transform one of the typical configuration here into one of the typical configuration here. It is a problem of symmetry. So in general, there are algorithms in which I can define a symmetry plane and then switch the system taking the mirror image with respect to this plane. So there is nothing that in a numerical simulation can forbid the system to sample the whole probability distribution, even though there is a factorization, even though there is an ergodicity breaking. And also the consequence of this is that you have seen that ergodicity is a postulate of statistical mechanics, but in the case of a phase transition, actually we are in many practical cases confined to a subspace with respect to the whole available space.